According to the National Electrical Code, when an equipment grounding conductor, often abbreviated as EGC, is installed, it must be continuous and effectively grounded. This means that the equipment grounding conductor must be connected to the grounding electrode system of the service equipment and run continuously to the grounded conductors of the equipment being supplied. In the situation presented, the existing triplex overhead feeding the utility pole does not include an equipment grounding conductor. The new gate motor requires a neutral and a ground. Therefore, to comply with the National Electrical Code, the triplex must be replaced with quadplex, and the equipment grounding conductor must be connected to the grounding electrode system at the service equipment. Grounding the system provides several benefits. Firstly, safety is increased. Grounding the system provides a low impedance path for fault currents, reducing the risk of electrical shock and damage to equipment. Secondly, equipment protection is enhanced. Grounding helps protect the gate motor from voltage surges and other electrical disturbances. Thirdly, conduit protection is achieved. If the wiring is run in conduit, the equipment grounding conductor will protect the conduit from becoming energized in the event of a fault. When performing the installation, several considerations are important. Firstly, quadplex cable selection is crucial. Use quadplex cable that is rated for the voltage and current requirements of the gate motor. Secondly, grounding rod installation needs consideration. The grounding rod at the utility pole should be driven to the required depth and in accordance with local codes. Thirdly, equipment grounding conductor connection is key. Connect the equipment grounding conductor from the quadplex cable to the grounding electrode system at the service equipment using appropriate connectors and clamps. Therefore, based on the National Electrical Code requirements and the specific needs of the gate motor, replacing the triplex overhead with quadplex and grounding the system back to the service equipment is required. This will ensure the safety and proper operation of the gate motor. The National Electrical Code addresses grounding extensively throughout several articles. Article 250 covers grounding and bonding. Section 250.4 describes general requirements for grounding and bonding, emphasizing the need for electrical systems to be grounded in a manner that limits voltage imposed by lightning line surges or unintentional contact with higher voltage lines, and that stabilizes voltage to ground during normal operation. Section 250.24 specifically addresses grounding separately derived alternating current systems. This section details how systems such as those powered by generators or transformers must be grounded, including the size and connection of grounding electrodes and grounding electrode conductors. Section 250.30 covers grounding requirements for separately derived alternating current systems in detail, outlining acceptable grounding electrode systems and the methods for connecting the grounding electrode conductor. Section 250.32 focuses on grounding requirements for buildings or structures supplied by feeders or branch circuits. It describes the conditions under which a grounding electrode is required at the separate building or structure and how the grounding electrode conductor should be sized and connected. Section 250.50 discusses the grounding electrode system and the various electrodes that can be used, such as metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, and ground rings. Section 250.52 details the specific requirements for each type of grounding electrode, including minimum lengths, depths, and installation methods. Section 250.66 provides guidance on sizing the grounding electrode conductor for alternating current systems based on the size of the ungrounded conductors. Section 250.118 lists acceptable types of equipment grounding conductors, including wire, cable, and metal raceways. Section 250.130 describes methods for connecting equipment grounding conductors, ensuring a low impedance path back to the source. In addition to these sections, other articles in the National Electrical Code provide specific grounding requirements for different types of equipment and installations. For example, Article 430 covers grounding of motors and motor control circuits, while Article 500 through 516 addresses grounding in hazardous locations. Article 680 details grounding requirements for swimming pools, fountains, and similar installations. These various articles and sections of the National Electrical Code work together to ensure that electrical systems are properly grounded and bonded, minimizing the risk of electrical shock and fire. When dealing with electrical installations, always consult the latest edition of the National Electrical Code and local codes to ensure compliance. Specific to the situation with the gate motor, several points from the National Electrical Code are directly applicable. Firstly, the requirement for an equipment grounding conductor to be installed with the supply conductors. Since the existing triplex does not include an equipment grounding conductor, it does not meet this basic requirement for new installations. Secondly, the need to establish a grounding electrode system at the utility pole location if it is considered a separate structure. This involves driving a ground rod and connecting it to the equipment grounding conductor. Thirdly, the proper sizing of the equipment grounding conductor based on the overcurrent protective device feeding a signal at the pole. This ensures that the equipment grounding conductor can safely carry fault current back to the source. Fourthly, the connection of the equipment grounding conductor to the gate motor itself. This connection must be made in accordance with the manufacturer's instructions and using approved methods. Fifthly, the inspection and testing of the grounding system after installation to verify its effectiveness. This can include measuring ground impedance and performing ground fault loop impedance tests. By following these guidelines from the National Electrical Code, the gate motor installation will be safe, reliable, and code compliant. Also note that local codes may have additional requirements that must be followed. Always check with the local authority having jurisdiction before starting any electrical work. Here is some additional information on grounding electrodes. Grounding electrodes are conductive objects that establish a direct electrical connection to the earth. They are a critical component of the grounding system, providing a low impedance path for fault currents to return to the source. There are several types of grounding electrodes recognized by the National Electrical Code. Firstly, metal underground water pipe. A metal underground water pipe that is in direct contact with the earth for at least 10 feet can be used as a grounding electrode. The water pipe must be electrically continuous and free of insulated joints or sections. A bonding jumper must be installed around any insulated joints or sections to maintain continuity. Secondly, metal frame of the building or structure. The metal frame of a building or structure that is effectively grounded can be used as a grounding electrode. The metal frame must be connected to the grounding system with a grounding electrode conductor. Thirdly, concrete encased electrode. A concrete encased electrode, often referred to as a U for ground, consists of at least 20 feet of bare copper conductor encased in concrete. The concrete must be in direct contact with the earth. The concrete encased electrode is typically installed in the footing or foundation of a building or structure. Fourthly, ground ring. A ground ring consists of a bare copper conductor encircling a building or structure and buried directly in the earth. The ground ring must be at least 20 feet in length and buried at a depth of at least 2.5 feet. Fifthly, rod and pipe electrodes. Rod and pipe electrodes are the most common type of grounding electrode. They consist of a metal rod or pipe driven into the earth. The rod or pipe must be at least 8 feet in length and have a minimum diameter of 5/8 inch for rods and 3/4 inch for pipes. The electrode must be driven into the earth to a depth of at least 8 feet. If rock bottom is encountered, the electrode can be buried horizontally in a trench that is at least 30 inches deep. Multiple grounding electrodes are often required to achieve a low enough ground resistance. The National Electrical Code requires that the resistance to ground of a single rod or pipe electrode not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional electrode must be installed. The two electrodes must be spaced at least 6 feet apart. The grounding electrode conductor connects the grounding electrode to the grounding system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The grounding electrode conductor must be made of copper or other corrosion-resistant material. The grounding electrode conductor must be securely connected to the grounding electrode using approved connectors and clamps. Proper installation of grounding electrodes is essential for the safety and reliability of electrical systems. The grounding electrodes must be installed in accordance with the National Electrical Code and local codes. The grounding electrodes must be inspected and tested to ensure that they are providing a low impedance path to ground. In the specific case of the gate motor installation, the grounding rod at the utility pole serves as the grounding electrode for the subpanel. This grounding electrode must be properly installed and connected to the equipment grounding conductor to provide a safe and effective grounding system. But remember that proper grounding is crucial for protecting people and equipment from electrical shock and damage. It is always best to consult with a qualified electrician to ensure that electrical systems are properly grounded. Let's delve further into the purpose of an equipment grounding conductor. The equipment grounding conductor, or EGC, is a vital safety component in electrical systems. Its primary purpose is to provide a low impedance path for fault current to return to the source, which facilitates the rapid operation of overcurrent protective devices like circuit breakers or fuses. This rapid clearing of the fault minimizes the duration of dangerous voltage on metal parts of electrical equipment, reducing the risk of electric shock. Here is a breakdown of its key functions. Firstly, fault current path. The equipment grounding conductor provides a low impedance path for fault current. In the event of a ground fault, where a live conductor comes into contact with a metal enclosure or the grounded part, the fault current flows through the equipment grounding conductor back to the source. Secondly, overcurrent device operation. The low impedance path provided by the equipment grounding conductor allows the fault current to quickly reach a high enough level to trip a circuit breaker or blow a fuse. This rapid operation of the overcurrent device isolates the faulty circuit and prevents further damage or injury. Thirdly, voltage limitation. By providing a low impedance path to ground, the equipment grounding conductor helps to limit the voltage on metal parts of electrical equipment during a fault. This reduces the risk of electric shock if someone comes into contact with the energized metal. Fourthly, equalization of potential. The equipment grounding conductor helps to equalize the potential between different metal parts of the electrical system. This reduces the risk of voltage differences that could cause electric shock. Fifthly, reduction of electromagnetic interference. The equipment grounding conductor can also help to reduce electromagnetic interference, often abbreviated as EMI, by providing a path for unwanted noise currents to flow back to the source. The equipment grounding conductor must be properly sized and installed to be effective. The size of the equipment grounding conductor is based on the size of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be made of copper or other corrosion-resistant material. The equipment grounding conductor must be securely connected to all metal parts of the electrical equipment. There are several types of equipment grounding conductors recognized by the National Electrical Code. Firstly, wire type. A wire type equipment grounding conductor is typically a bare or green insulated copper wire. It is run along with the circuit conductors inside a raceway or cable. Secondly, metal raceway. A metal raceway, such as conduit or electrical metallic tubing, or often abbreviated as ENT, can be used as an equipment grounding conductor. The metal raceway must be electrically continuous and properly connected to the electrical equipment. Thirdly, cable armor. The metal armor of some types of cable, such as armored cable, often abbreviated as AC, or metal-clad cable, often abbreviated as MC, can be used as an equipment grounding conductor. The cable armor must be properly connected to the electrical equipment. Fourthly, equipment grounding conductor in cable. Some types of cable, such as non-metallic sheath cable, often abbreviated as NM, include a separate equipment grounding conductor. This equipment grounding conductor is typically a bare copper wire. In the specific case of the gate motor installation, the equipment grounding conductor in the quadplex cable provides the low impedance path for fault current back to the source. This equipment grounding conductor must be properly connected to the grounding electrode system at the service equipment and to the gate motor to ensure a safe and effective grounding system. Always consult the National Electrical Code and local codes for specific requirements on equipment grounding conductors. Proper equipment grounding is essential for the safety and reliability of electrical systems. And now, let's discuss the function of a neutral conductor in an electrical system. The neutral conductor is a critical part of a single-phase or three-phase alternating current electrical distribution system. It serves primarily as the return path for current from the load back to the source, and it is typically grounded at the source, which establishes a reference point of 0 volts. This grounding is what differentiates the neutral from the equipment grounding conductor, which is strictly for safety during fault conditions. Firstly, current return path. In a single-phase system, the neutral conductor provides the return path for current from the load back to the source. The current flows from the source through the hot conductor to the load and then returns to the source through the neutral conductor. Secondly, voltage stabilization. By being grounded at the source, the neutral conductor helps to stabilize the voltage in the electrical system. This grounding provides a reference point of 0 volts, which helps to prevent voltage fluctuations and imbalances. Thirdly, reduction of harmonic distortion. The neutral conductor can also help to reduce harmonic distortion in the electrical system. Harmonic currents, which are caused by nonlinear loads, can flow through the neutral conductor and back to the source. The neutral conductor must be properly sized to carry the expected neutral current. In some cases, the neutral current can be as high as the phase current. The National Electrical Code provides guidelines for sizing the neutral conductor based on the type of load and the expected harmonic content. The neutral conductor must be insulated to prevent accidental contact with grounded surfaces. The insulation is typically white or grey in color. The neutral conductor must be securely connected to the neutral bus at the service equipment and to the neutral terminals at the load. In a three-phase system, the neutral conductor provides a return path for unbalanced currents. If the loads in the three phases are not equal, the neutral conductor will carry the difference in current back to the source. The neutral conductor is essential for the proper operation of many types of electrical equipment. Many appliances and electronic devices require a neutral connection to function correctly. The neutral conductor also plays a critical role in ground fault protection. In the event of a ground fault, the current will flow through the neutral conductor back to the source, which will trip the circuit breaker or fuse. In the specific case of the gate motor installation, the neutral conductor in the quadplex cable provides the return path for current from the gate motor back to the subpanel. This neutral conductor must be properly sized and connected to ensure the proper operation of the gate motor. It is important to note that the neutral conductor and the equipment grounding conductor are separate conductors with different functions. The neutral conductor carries current during normal operation, while the equipment grounding conductor only carries current during a fault. The neutral conductor is grounded at the source, while the equipment grounding conductor is connected to the metal parts of the electrical equipment. Always consult the National Electrical Code and local codes for specific requirements on neutral conductors. Proper installation of neutral conductors is essential for the safety and reliability of electrical systems. Now, we'll focus on the importance of using quadplex cable instead of triplex cable in this scenario. The key difference lies in the presence of an equipment grounding conductor in quadplex cable. Triplex cable typically consists of 3 conductors, 2 phase conductors and a neutral conductor, but lacks a dedicated equipment grounding conductor. In contrast, quadplex cable includes these 3 conductors plus a 4th, the equipment grounding conductor. This equipment grounding conductor is essential for safety and compliance with the National Electrical Code, as previously discussed. Firstly, safety. The equipment grounding conductor in quadplex cable provides a low impedance path for fault current, reducing the risk of electric shock and equipment damage. This is particularly important for outdoor installations like gate motors, where exposure to moisture and other environmental factors can increase the risk of ground faults. Secondly, code compliance. The National Electrical Code requires that all new electrical installations include an equipment grounding conductor. Using quadplex cable ensures compliance with this requirement. Thirdly, equipment protection. The equipment grounding conductor helps to protect the gate motor from voltage surges and other electrical disturbances. This can extend the life of the motor and reduce the need for repairs. Fourthly, future-proofing. Using quadplex cable provides a future-proof installation that can accommodate changes in the electrical system. For example, if the gate motor is replaced with a different model that requires an equipment grounding conductor, the existing quadplex cable will already be in place. When selecting quadplex cable, it is important to choose a cable that is rated for the voltage and current requirements of the gate motor. The cable must also be suitable for the environmental conditions in which it will be installed. Quadplex cable is typically more expensive than triplex cable, but the added safety and code compliance make it a worthwhile investment. In the specific case of the gate motor installation, replacing the existing triplex cable with quadplex cable is necessary to meet the requirements of the National Electrical Code and to ensure the safety and proper operation of the gate motor. Skipping this step could result in a hazardous installation that could put people and property at risk. Therefore, the decision to use quadplex cable is not just a matter of preference, it is a matter of safety and code compliance. Always consult with a qualified electrician to determine the correct type of cable for your electrical installation. In addition to the above points, consider the potential liability associated with using the incorrect type of cable. If someone is injured or property is damaged as a result of a faulty electrical installation, the installer could be held liable. Using quadplex cable and following all applicable codes and standards helps to minimize this risk. Furthermore, the use of quadplex cable can improve the overall reliability of the electrical system. The equipment grounding conductor can help to prevent nuisance tripping of circuit breakers and other electrical problems. In conclusion, the benefits of using quadplex cable far outweigh the additional cost. It is the right choice for the gate motor installation and for any other electrical installation where safety and code compliance are paramount.